about some global properties of the modular space of Calabi-Yau manifold. But before I do that, let me first answer the question raised by Professor Tu and King Ichi yesterday. So let me change my slide first. There's some leftovers for yesterday. Okay. So one thing is that in algebraic geometry, when we talk about the modular space of a compact Kähler manifold, we need to have usually the modular space has to be polarized. This is because a big theory of Mumford which state that the modular space of a polarized compact Kähler manifold is a complex variety, and so this is a global theorem. On the other hand, by Codella, Spencer, and Kronish, we know that the local deformation space of any compact complex manifold is always an analytic set. But globally, it may not even be a Hausdorff space. So that's the major difference. So by what we discussed yesterday, for any fixed Calabi-Yau manifold, compact Calabi-Yau manifold X, the deformation space or the Kronish space of X is always smooth. It is actually an open set of this vector space H1X Tx, which is the space of harmonic Tx valued 0, 1 form. So there's no polarization needed in his theorem. But what we need, if we insist that the deformation keeps the polarization, then actually the Kronish space or the infinitesimal deformation space is not that. It will be a little bit smaller than such a space. So assuming that our Calabi-Yau manifold is simply connected, then its first Hahn class always determine there's one-one correspondence between the first Hahn class and the polarization. So for fix such a line boundary is equivalent to fix the cohomology class of omega. And then using that omega, we can define a subset, subspace of this vector space, which composed of all phi such that L phi omega is equal to 0. And here, when we say L phi omega equal to 0, what we really mean is, if in local coordinates, it is as follows. Phi is written as phi ij bar d dzi, something like that. And then we use the Kähler metric, the Kähler form, to contract it. If we use the Kähler metric to pull this index down, then we will get a 0, 2 form. And so this L phi omega equal to 0 means this L phi omega in the cohomology group is 0. It's not really 0. It's coboundary. It's D-bar coboundary. Okay? So we mean that in the cohomology class case. So by definition, this should be a subspace of it. But in most cases, actually, this space is equal to that. Okay? For example, if we assume the Calabi-Yau manifold is simply connected, so then this is equal to 0. So is H10, and by the Serre duality, H20x is equal to 0. And this defines a class in this space. If this space is 0, then everything has to be 0. Okay. So in most cases, or at least in the case we are interested, for example, Calabi-Yau threefold, simply connected Calabi-Yau threefold. So any deformation keeps the polarization. Okay. Well, even though this H1 omega space is a proper subspace of H1, then we still have the following argument. So assume that the Ricci-Flat metric is given by Gij with a given polarization. So remember, by our original deformation of the Weil-Petersen metric, we can only define the Weil-Petersen metric when the matrix on the fiber is fixed. Okay, and that needs a polarization. Or in other words, we can only define. So two facts. So number one is the Weil-Petersen metric is only defined on the smaller space H omega 1 xtx. And number two is no matter what happened, this one defines a Kähler metric on the Kronish space. Or in other words, this defines an inner product on H1 xtx. So what Tian's theorem really means is that when we restrict such a Kähler metric from this space to this smaller space, then it is equal to the Weil-Petersen metric. Okay, so let me give a very quick proof. It's actually a straightforward computation. So in fact, it's interesting because in the Calabi-Yau case, we can actually write down the Cadet-Spencer map. So assuming that we have polarization so that we have a family of Ricci-Flat metric Gi bar, and assuming that we have a family of 3-0 forms holomorphically depending on the parameter t, and then we can define the following map, which is the Cadet-Spencer map. So dd t alpha is a vector on the modular space, and we use that to produce a 2-1 form, which is defined by the derivative of omega with respect to t alpha, and this one, and take the 2-0 component of that. So so this is a 2-0 form, but we know that on Calabi-Yau threefold, this 2-0 form is equivalent to, can be identified to the vector valued 0-1 form. Okay, so I'm sorry, this is 1. I made a mistake. This is 1. Okay, so this one actually gives us the Cadet-Spencer map, and so one reason we can okay. So this defines the Cadet-Spencer map. So let's do some computation. So if we compute this directly, let's put the following way. So let's assume Q omega bar is equal to the integration of omega wedge omega bar. So then there is a straightforward computation. Log Q omega bar. This is equal to negative omega bar d alpha omega d beta omega bar, then plus omega bar square, and d alpha omega bar multiplied by omega d beta omega bar. So this is straightforward computation. Just expand this, take second derivative. But we can rearrange these terms. Essentially, if we write this d alpha omega by Griffith's transversality, omega is a 3-0 form. When you take derivative of it, you get at most two components. One is 3-0 form, one is 2-1 form. This is Griffith's transversality. So we can actually write d alpha omega minus k alpha omega plus k alpha omega. Just to choose the appropriate function k alpha so that this part belongs to a 2-0 form and that part belongs to a 3-1 form. Just take orthogonal decomposition. And the k alpha is determined by that this one is perpendicular to that one with respect to the quadratic form Q. And with that in mind, we can rearrange this expression and write it in that way. Okay, so just like I said. Okay, so next is the key. So when we assume the Calabi-Yau manifold is simply connected, so then H21 is primitive. So primitive basically means that the harmonic form in this space is not a wedge, is not of the form of another phi wedge omega, where omega is the Kähler metric. Because if it is, then phi has to belong to H10. This is 2-1. And the H10 is nothing, it's 0. So every element in this cohomology group is primitive. And when some cohomology class or when some harmonic forms are primitive, then the trick is this wedge, Q of something means wedge, and the integration, it's actually equal to the inner product. So this is for primitive, up to a constant. So phi wedge phi bar is equal to phi inner product is phi and the dvx, up to a constant. So that tells us that this one, the left-hand side, is from this, okay? dd bar log q omega omega bar. And the right-hand side, you can imagine this is the standard way to define the L2 metric or the Weil-Petersen metric, right? This is pointwise inner product, then integration against the whole manifold. So it's the standard way of defining the Weil-Petersen metric. And because of this primitiveness, then we know that even though the right-hand side depends on the Ricci-Fred metric, the left-hand side does not. Okay, so this gives us the proof. Okay, so the conclusion is this metric, which is always scalar, is well defined on the Kronish space without polarization, and its restriction to any modular space of polarized modular space defines the Weil-Petersen metric. But in a lot of cases, we are interested, so we don't have to worry because these two spaces are actually the same if H20 is 0, or if in the Calabi-Yau-3 case, if we assume that the manifold is simply connected. Okay, so that's all for the question. But we still don't know globally, even if this is satisfied, even if this is satisfied, then for different polarization, for Calabi-Yau manifold, for different polarization, locally they are even isometric, but globally we don't know. The reason is that, probably the reason is that if we have one family of degeneration of Calabi-Yau, with the central fiber is also a Calabi-Yau manifold, then we can replace it by another Calabi-Yau, which makes everything still smooth. So that's the difficulty. So the global property is always difficult to define. And in fact, the definition of the modular space itself requires a lot of extra work, which is quite different from defining the Kronish space. Okay, so this is, I hope that answers the question. All right, so today we are going to talk about some global properties of the modular space of Calabi-Yau threefold or Calabi-Yau n-fold. So to some extent, it's quite difficult to study the global differential geometric properties. So I restrict myself to differential geometric properties because there are a lot of studies in algebraic geometry, and algebraic geometry from very beginning is global. Okay, so differential geometry is different from algebraic geometry in that aspect. We first need to study local properties, then go to global. One thing which is very bad to us is that so far we don't have an answer. We cannot answer the following question: is there a condition that ensure that the modular space of Calabi-Yau manifold is complete? Okay, so that question actually is interesting because number one is the counterpart of Calabi-Yau manifold is the so-called modular space of Calabi-Yau manifold is the so-called special Kähler manifold, and we already proved that special Kähler manifolds, most of them cannot be complete, other than if they are not flat, they cannot be complete. So for Calabi-Yau manifold, this is actually related to another question, another conjecture in algebraic geometry, namely if. So this is what we know. So given any Calabi-Yau manifold, can you degenerate this Calabi-Yau manifold to a singular Calabi-Yau manifold with only rational double point? So this is a conjecture. The conjecture is this should be true, okay, under some assumptions. Well, if this were true, that would imply that any modular space of Calabi-Yau manifold is incomplete. The reason is that if you draw a curve between x to x prime and you compute its Will-Peterson distance, and then you will see that the distance has to be finite. So that means it is incomplete. So in other words, study the question whether the modular space of Calabi-Yau manifold is always incomplete can be considered as a weaker conjecture than this big conjecture. Okay. So what we know is even you can degenerate a Calabi-Yau manifold to terminal singularity, the distance to that Calabi-Yau is still finite. Only when you have to degenerate a Calabi-Yau manifold to a very singular Calabi-Yau manifold, then you would have infinite distance. So I'm not going to talk details about that. So it is believed that at least for all the known examples, the modular space of Calabi-Yau manifold is incomplete. Okay, so that would raise another question: how about the Hodge metric? And we don't know, and it's interesting to study that portion of that direction of the problems. So if completeness is generally not true, then probably the only way to study the differential geometry of modular space of Calabi-Yau is to study its Chern class, is to study its characteristic class. So because of that, let me give a very quick review of characteristic class or Chern classes. So let's assume that M is a compact complex manifold, and let's assume that E is a holomorphic vector bundle over that compact complex manifold. So, of course, in order to define Chern classes, we don't have to assume to make M and E so restrictive. But let's assume that. So, and then assume that H is a Hermitian metric on the holomorphic vector bundle, so that the holomorphic vector bundle becomes a Hermitian bundle. So then, because everything is holomorphic, so the connection and the curvatures are so easy to write down. So namely, if you fix a frame and write H as a Hermitian matrix, then we can write out the connection matrix, which is a matrix valued one form as DH minus. And the curvature is just the D bar of gamma, is the D bar of the connection. So that's well known. So now let F be an invariant polynomial on the space of